Thank you for the introduction and welcome to my talk. So when we conduct structural integrity assessment via damage mechanics on a macroscopic scale, we usually combine modified Weibull-Zwicky model for ductile damage and a generalized Ovan model for cleavage. And then this combined model is able to describe the macroscopic toughness properties by limit strains. And that is independency of the stress triaxility eta and the load angle parameter theta bar. So we end up with certain loci. So the lowest one is typically the MCI locus, which stands for microcrack initiation, so the cleavage locus, followed by DDI, which stands for ductile damage initiation, and DF, which stands for ductile failure. To calibrate those loci, a bunch of different sample geometries has to be tested to obtain some porting points for different stress states. So it's quite material and time consuming. And also that means that a certain volume of the material is needed to characterize it. And of course, we assume a homogeneous behavior over the material. Now the question can be raised how to deal with inhomogeneities. So basically different zones in the component of a different microstructure, which can be quite small, but significantly influence the overall properties of the component. So therefore, the aim in this work was to derive a simulation concept to obtain macroscopic toughness properties directly from the microstructure, which has some benefits. For example, that we only need a low material input and can calibrate the macroscopic model parameters for the present material, so for the present aging and damage state. And this simulation concept consists of 4 steps. The first one is the generation of a microstructure model, as already introduced by my colleague. So-called representative volume element of the microstructure. The second step is the calibration of a material model to obtain some mechanical properties. The third step would be to define some damage criteria on the micro scale. And then in the fourth step, bringing all that together, virtual experiments can be conducted to derive damage model parameters for the macro scale, for the macroscopic model. I derived the simulation concept for the material 22-9-Macros-U7, which is a reactor pressure vessel steel. In general, it's ferritic bainitic, but as you can see in the kernel average misorientation map, there are only a few uniform blue-colored grains. So the amount of ferrite is not, or is usually less than 5%. And therefore, I also made the assumption to neglect that and assume pure bainite. And regarding the hierarchical substructure of bainite, it was not that pronounced, so we were not able to reconstruct it. But in general, Dragon is able to deal with multiple phases and also with substructures. But in this case, for simplicity, we assume just a pure bainitic steel without a substructure. So my colleague already introduced you the concept how to generate a microstructure model. So we start with an EBSD, fit some ellipses to get quantitative microstructure data. Here I use the OEM analysis software from EDAX. Then this quantitative data is fed. Oh, that was too fast. Yeah. Then this synthetic data is fed into the Wasserstein gun to obtain a synthetic data generator, which can then be used for Dragon to generate RVEs. I created a bunch of RVEs for my simulations, which could look like this. Coming to the second step, we only have now a geometrical model, so we need some mechanical properties which have to be assigned to the geometrical model. And therefore, I've used a phenomenological crystal plasticity model, which is implemented in the user subroutine in Abacus. And I've added a strain rate and temperature dependency, which follows the macroscopic behavior of the material. And the calibration looks like that. Since I assume a pure bainitic material, I could do an iteratively inverse calibration on uniaxial tensile test And as you can see, I mainly focus on the stress strain behavior at higher strains. So this pronounced yield strength followed by the steep increase due to the hardening. This is quite hard to model, or kind of impossible to model with the subroutine. And since I'm interested in ductile damage initiation, I focused more on the behavior for higher strains. Yeah, here you already saw the uniaxial tension stress state, but it's also possible to apply different periodic boundary conditions to get different, or to set different stress states on the RVE. For example, plane strain, shear, or biaxial tension. And as you can see, this is a CPFEM in Abacus, but similar things could also be done in Damask or the FFT solver, as mentioned previously. Yeah, investigations on my material were made in the past where ductile damage initiation was observed mainly on non-metallic inclusions. So some kind of localization criterion would be suitable here. And for cleavage, it was observed that hard particles were breaking, as well as higher dislocation densities around the grain boundaries. But also, and which is probably more important, is the crack arrest and blunting in the benetic phase. So this is then the critical step for the cleavage damage, and therefore fracture stresses of the individual constituents of the microstructure would be a suitable criterion on the microscale. Yeah, those damage initiation criteria were defined and applied in the post-processing script, so not in the simulation itself. And for cleavage, I used a maximum principal stress criterion. So the criterion is fulfilled as soon as any grain in the RVE reaches an average maximum principal stress of a certain threshold value. And the threshold value for my material is 1500 megapascal as lower bound and 1900 megapascal as upper bound, as observed in previous studies. For the ductile damage initiation, I took the maximum force criterion as damage initiation criterion on the microscale, which is a quite simple one, but probably suitable for this material. So here I've checked the first Euler-Kirchhoff stress for the maximum, which is first Euler-Kirchhoff stress is also referred as engineering stress. So basically the maximum in the curve. And yeah, as soon as one of the criteria is fulfilled, the plastic equivalent strain is calculated as an average over the whole RVE. And then together with the analytical solutions for the stress states, so for stress triaxility and the load angle parameter, I obtained supporting points in the stress state space. And then the macroscopic loci can be fitted to those supporting points. And to consider scatter, I've simulated a bunch of RVEs, which are geometrically different. So they are always freshly generated RVEs, but the statistics behind that is the same. So for ductile damage initiation, that are the results. So as you can see, the colored scatter dots are from the RVE simulation, and this gray grid is a classical experimental numerically calibrated locus on the macro scale, but so that we can compare it. It's kind of the validation. And as you can see, for uniaxial tension and plane strain, that fits quite well, or is in quite good agreement with the macroscopic locus. But for shear and the biaxial tension, those values from the RVE simulation are way higher compared to this locus, which can be probably explained by this used criterion, quite simple criterion for the ductile damage, which was the maximum force criterion. And here I've plotted force over displacement for our macroscopic shear samples. And as you can see, at the maximum force, we usually observe already ductile failure, and the ductile damage initiation happens way earlier. So that is probably not the correct approach for the shear stress state. And for biaxial tension, so for the green dots, the experimental validity of this macroscopic locus is only given in the region for theta bar values larger than 0, because I only conducted tensile tests to fit this locus, and then I assume a symmetrical extrapolation of this locus. Therefore, some biaxial tangent tests have to be performed for a good or for proper validation. Right now, I just assumed a symmetrical locus, but there are also asymmetric loci or loci descriptions in the literature. So yeah, I have to check that in the future. And then for the microcrack initiation at -196 degrees C, you can see when you look at the scale, quite low PEQ values for the microcrack initiation, which is not in agreement with what we observed macroscopically. So for our macroscopic experiments, we observed for this material ductility before the cleavage fracture. And yeah, probably one reason is that, especially in the beginning, there's quite big offset between the experimental curve and the simulated curve of 250 megapascal, and therefore the maximum stress, maximum principal stress criterion is fulfilled way earlier, which leads to smaller PEQ values. So yeah, here I have to rework on the temperature extrapolation approach from the room temperature to -196 degrees C. Yeah, that's it. So to sum it up, I've presented a macroscopic. I've presented a simulation concept to derive macroscopic toughness parameters from the microstructure, and that is, in the end, also our overall aim to go somehow from the microscale to the macroscale. Yeah, that's it. Thank you very much for your attention.